So this will be the last lecture, and I'm going to talk a bit briefly about deep learning, neural networks and deep learning, but mostly from a perspective of unsupervised learning. So I'm going to talk a bit about the problems of deep learning, but then we'll focus on some solutions that were found for trying to solve these problems, but that are also useful for unsupervised learning with neural networks. So basically we're going to see at what is deep learning, why it could be an advantage, and the problem with backpropagation if we use the standard types of activation functions that we saw when we saw the neural networks part. Then we're going to look at autoencoders, which was one of the first solutions found to try to train deeper networks, but which are also interesting because of the way they can be used in unsupervised learning. And we're going to see this idea of stacking denoising autoencoders to build deeper networks, although currently with deep learning this is no longer very used. There are other approaches. But the interesting part about the autoencoders is mostly the unsupervised learning. So in theory, with one hidden layer, we can approximate any function, at least within some finite interval, using one hidden layer of an artificial neural network. So we can arbitrarily approximate any function within a finite interval. So basically we can adjust the weight of the hidden layer to model each little part, each little segment of the function, and we can increase the complexity of what we can model just by increasing the number of neurons in the hidden layer. So basically, if we have no limits to the neurons in the hidden layer, we can use an artificial neural network with one hidden layer to fit any training set, any reasonable training set that we have. The problem is overfitting. When we increase the number of neurons in the hidden layer, we are increasing the number of dimensions where we are projecting our data into, and we saw that this leads to overfitting. With deep networks, we can avoid part of this problem when we use a stack of hidden layers, but we can avoid having any of them much larger or arbitrarily large, so we can keep the number of dimensions we are projecting into at a reasonable size, and each layer will transform the input space in a different representation until eventually the network finds a good representation for whatever classification task it is trying to do. So this is generally how we solve problems too. We don't have an arbitrarily complex system all at the same level. We build things, for example, hardware, then drivers in the operating system, then kernel and so forth, applications. For example, when we are trying to make a computer work, it's not an arbitrarily complex thing all at the same level, but a stack of elements that will transform from one level to the other. So this is generally an idea of how artificial neural networks could work, and it seems to be also how our brain works. So the architecture of the neural networks that we have follow this layered approach, where the retina cells in our eyes, which are actually part of the brain too, so the visual part, the eyes, is also grows from the same tissue as the brain. These retina cells will find color and brightness. Then we have ganglia that extract information from regions from several retina cells and identify edges and orientation, so a different level of representation. Then we reach the visual cortex, where these patterns can be matched to things in memory and identify different elements. And then we have the motor cortex that can enact the appropriate behaviors and encode for what actions we may follow. So these are all stacked in different layers at a considerable depth sometimes, where different representations will be used by different layers at each different stages of the process. So, unfortunately, when we try to model this with the standard types of networks that we saw, when we use those sigmoid activation functions to simulate what our neurons do, and then we apply backpropagation to reduce the error, we cannot fit artificial neural networks that have many layers. Now, this is not very surprising because backpropagation is a very artificial algorithm, which is certainly not what our brain is using. So our brain is not trying to minimize the error function by going down the derivatives of the function and so forth. But it's a problem because this is a very good algorithm that we have, and when we try to do backpropagation on these kind of nonlinear neurons, we have these difficulties. So this is an example of classifying this data set with a neural network that has one hidden layer with two neurons. We see that in about 650 epochs we can train the network. We have the profile for the training error. And what happens here is that this division between the two sets can be achieved because the neurons in the hidden layer are transforming that representation, that distribution of points, into this one where we have all the crosses over here and the circles over here, so we can cut, the final neuron can cut with a straight line at this part and separate the two classes. So this is a shallow network. It has only one hidden layer, the input, the hidden layer, and the output. If we have a more complicated problem, so in this case we have a more intricate mix of these crosses and circles, using one hidden layer, this takes the error goes down here at first, but then it stabilizes and the network cannot learn to separate these classes. So even after some 2500 epochs, so each epoch is one pass over all the data set, it still cannot separate the two because the hidden layer is unable to transform this data in a way that then can be separated linearly. So it's still there is still a mix of circles and crosses there, and the final neuron cannot separate them. So one way of solving this problem without increasing the depth of the neural network would be simply to increase the number of neurons in the hidden layer. This will effectively be projecting that data set into a higher dimension using a nonlinear projection, because all of these neurons have a sigmoid activation, so they provide a nonlinear transformation, and then we could be able to classify this, but the problem is that increasing the number of dimensions will also increase the risk of overfitting. So in some cases it may work, in other cases it will be worse. One thing we can do alternatively is keep everything in 2 dimensions, but add another layer. So we're going to add another hidden layer of 2 neurons too, and try to make the following, the next layer, transform this part further in order to be able to separate those 2 classes. Now the problem here is that it takes a lot longer to start to learn. So at first it was around 600, now it goes to 3000, and then eventually we even get some problems there. So this implementation is not very good, but you can see here some instability, numerical instability at the end. And we cannot still after nearly 10,000 epochs, we still cannot find a way of classifying this set. So what's happening here is that the second layer can only start doing something interesting after the first layer has started to transform the data. So in the beginning, if you see here, the first layer, if it's not doing anything, then the second layer cannot do anything with that data either. Unfortunately, the arrow must be propagated backwards all the way to the first layer, and then as the first layer starts transforming the data, the second layer can start learning something interesting, and this takes a lot of time. And eventually, even after many epochs, the second layer has still not learned anything that is useful. we can add another layer, 3 hidden layers, but this only makes things worse. So now we need to go up to 30,000 epochs to get a slight decrease in the error, but it still doesn't do anything that can closely classify this data set. And the problem here is even worse, because now the second layer must wait for the first one, and then the third layer must wait for the second one before it can do anything interesting with the data. And this is especially bad because of the way the neurons respond. So if you remember, that sigmoid activation function is flat at the extremes and changes abruptly in the middle, and this is why we use it. It's a nonlinear activation function, and it mimics what the brain cells, the neurons do, that they are silent up to some threshold, and then they fire with a fixed intensity. But when we try to propagate the derivatives of the error in backpropagation, if we are at that flat region where the sigmoid function is saturated, then the derivatives are very close to zero. And since we have to propagate by multiplying the derivatives between the layers, the more layers we have, the smaller the overall value will become, because we are multiplying numbers that are almost zero in any case. So eventually, this is called the vanishing gradient problem. The gradient disappears as we go along the network, and things take too long to train, or impossibly long to train. So one thing that really revolutionized this in the past few years is the use of these rectified linear units, which are much simpler activation functions. So basically, the output is the same as the input over the threshold, but zero below the threshold. So you have something that has a linear response, but only after some threshold is passed. And this allows us to solve this vanishing gradient problem, because now, if the neurons are active, the derivative is constant and does not disappear. And this allows the network to train much faster, and we can use deep neural networks in this way. However, this is no longer remotely similar to what happens in biological networks, because we don't have this linear response in the neurons, and we went outside trying to model what the brain does. There are other techniques here that also can help, like using higher derivatives and momentum and so on. So this is what is usually done to solve this problem nowadays. But for some years, before these kinds of activation functions were discovered, or the usefulness of them was discovered, there was another interesting way of trying to train the network, which is first pre-training layer by layer. So you can see the problem here, that it takes a lot, during a lot of time in training the network, these layers are not doing anything, because they have to wait for the first one to learn some transformation of the data. And then the second one must learn something, and then the third one, and so on. So the idea was that we would train first one layer of the network to try to transform the data in some way, and then use that transformation to train the second layer, and then the third, and train each one separately. So how can we do this? The way to do this is with unsupervised learning with autoencoders. And the idea of an autoencoder is an artificial neural network that is trained to give as output the same thing it receives as input. This is an example of an original version of the autoencoder. It was called Autoassociator by Mitchell. And this is a very small example, but it's easy to understand. We have the inputs here, which can be zeros and ones, but only one of the inputs can be one, and the output has to be the same. So we are training the network for that. But there are only 3 neurons in the hidden layer. So the network must somehow encode these 8 possible values into combinations of these 3 neurons. And this is basically forces the network to learn binary encoding of the 8 possible values. So basically, we can do this. We can train the network that has to output the same as the input, but controlling the architecture of the network inside, we can force it to represent the data in some particular way. So one thing we can do is to reduce the dimensions of the data, so create a more compact representation. This is an example of work by Hinton in 2006. So this was before the rectified linear units, and where there was a lot of research into autoencoders. But this was done then to reduce the dimensionality of the input data and represent it into dimensions. The input data is that handwritten digit data set from NIST. So this is the images are 28 by 28. They are a bit larger than the example you have on scikit-learn, but it's the same data set with the handwritten digits. So this is 784 inputs for each image. And this is the dimensionality of the data set. Each example has 784 dimensions. Using principal component analysis, we can find the two directions that have the largest variance, and then we can plot the data here. So here in different colors we have the different digits, and this is basically a messy cloud with everything mixed together. But what they did was create a neural network that starts with these 784 and has 1,500, 250 neurons and 2 neurons in the middle. And then it goes back again, 250, 500, 1,000 and the 784. Then they train this network to output the same thing as the input. So try to recreate the same images of the handwritten digits, but with only 2 neurons in the middle. After training the network, so it could recreate the images after passing through these 2 neurons, they threw away the decoder part, so the other part of the network that restored the input as output, and projected everything into these 2 neurons. So here we have the result, and here we can see that the different digits are much better separated in the activation of these 2 neurons in the middle of the network. So autoencoders can learn a representation of the data in an unsupervised manner. We can use the same input as the output and try to force the network to create a different representation of the data inside. And this can then be used as to pre-train a deep network, or simply to reduce dimensionality here. So in general, autoencoders tend to minimize this loss function, which is the error between the input to the network and the output of the network. So the output is supposed to be the same as the input. They tend to be symmetrical. We have the same number of layers up to the middle, and then going back again to decode the same that representation. And the dimension of the hidden of the mid layer where we are encoding this new representation can be smaller if we want to compact and reduce dimensionality, or it can also be larger. We can expand the dimensions in that way, although there is the problem of overfitting if we do that. One variant that is particularly useful to reduce the overfitting problem is the denoising autoencoder. So we are training the autoencoder in the same way. The output must be the same as the input. However, every time we present an example to the network, we randomly set at 0 a random set of inputs. This means that the network not only must be able to encode or encode differently our inputs, but also restore the missing data. So those zeros, the network must be able to figure out what values they must have in order to restore the original data and minimize the error to the original vector. So this allows us to train parts of the network by creating an autoencoder, training some representation of the data, and then throwing away the decoding part and using only the encoded representation as the input to the next layer. And this way we can stack these denoising autoencoders, for example, or any set of autoencoders, and build a deep neural network out of these local autoencoders trained only a few layers at a time. So this was one of the ways of training deep neural networks before using rectified linear units. and it's still interesting from an unsupervised learning perspective, because all of these layers were trained in an unsupervised manner. So basically, we train an autoencoder on the original data. It has to output the same as the input, but we can add, for example, noise and force it to denoise the data and generalize better. Then we discard the decoding layer, and now we only have the encoding part, and we have a new representation of the data. So this is now our new data set that we use to train another autoencoder, in the same way, trying to obtain the same thing as we input to that network. And then we throw away the decoder part, and we keep stacking these trained autoencoders until we eventually have some re-encoding of the original data that is particularly useful for our classification task. So all these autoencoders are trained without trying to classify or something, because we are doing it unsupervised, in an unsupervised manner, but eventually we may reach a representation that makes it easier to classify our data. This is an example. If we re-encode the 784 length vectors of the images into this two-dimensional representation, it is much easier to separate the digits than in the original data. And then at the end we can fine-tune the neural network with backpropagation, because now we already have the layers pre-trained to be close to a useful final solution, and that let us avoid that problem of each layer having to wait for the previous one to learn before starting to learn something. However, nowadays this is mostly not used when training deep neural networks because of those new techniques of new activation functions and so on, which allow us to train everything with backpropagation from the beginning. So there are some advantages, significant advantages of deep learning, which are, most of all, we don't need to worry about engineering the features. So thinking about which features to use, selecting features and so on, we just dump everything into the network and let the network figure out what to do with the data. So this means more unemployment, but makes it much easier to train with very complex data, like sounds, images, text, and so on, where it's hard to figure out which features we should use to train the classifiers. It's also very adaptable and allows us to transfer knowledge. For example, if you have a deep neural network trained to classify images into cats, dogs, and birds, and boats, and so on, most of the network, what it's doing is extracting useful features from the images. So if you throw away the last part of the network and replace it with some other classifier, you can probably use a lot of that process to train a classifier for other kinds of images, like digits or types of cars or species of birds or things like that. So it's easier to use parts of the network and adapt and transfer knowledge from one domain to the other. The problems with deep learning. One thing, it requires a lot more computation and data. So the big advantages of deep learning were revealed once enough data was collected. So when there were these challenges of image classification using, for example, 2,000 images or 5,000 images and so on, deep learning never beat other more classical methods. But once they reached about 200,000 images, then deep learning was much better than anything else, and that's basically the requirement. You need to have a lot of data for this to work. Another disadvantage is that after you train your model, it's very hard to understand what's going on. So why exactly the network is classifying this example in this way or that example in that way. So one particularly funny example from the beginnings of this kind of research was a neural network trained to identify when a person was standing next to a car. So they photographed cars without anyone around and photographed cars with people close to the car, and then the network was trained and could distinguish between the two very well. but then they figure out what the network was doing. They photographed the examples at different times of day, and the network was figuring out that some photographs were lighter than others. So it was merely looking at the brightness of the photograph and classifying that according to that criteria. So it's hard to say what the network is doing, and we need to be careful with our data set and with whatever is happening there, because we have little control over the features that are being used. Another thing that we can do with deep neural networks, this is a way of visualizing what the network is doing. So in this particular method, the image is passed through the network that is trying to identify something. For example, this is a network trained to identify dog faces, and they pass the image of the spaghetti dish through the network, and they saw which part had a slightly higher activation. And then we can compute what to change in the inputs to increase that activation a bit more, and so we can change the image to maximize those slight activations the network has. So this is representing what would make the network identify in that image the dog faces that it was already half identifying when it was looking at the image. In this case, it's a network trying to identify eyes and doing the same thing there. So we can, there's a lot of research in trying to visualize what the network is doing, and also we can use the network in this way to change images and to generate new images. There is one example where you can use a photograph of, say, a sunny day, and then choose to make it rain, and the network changes the image, and it seems like it's raining. And there are also these deep fakes where they create videos with the photograph of one person over some other actor or some other videos and so forth. So there's a lot of different applications for this technology. So to sum up, we looked at first at artificial neural networks as classifiers using those sigmoidal neurons that mimic the way the brain works. However, if we use these activation functions that saturate, then backpropagation cannot work over many layers. However, we know that there are some other ways of training the network, like using pre-training, but mostly for modern day uses, what is done is to use other nonlinear activation functions, such as the rectified linear unit, that is linear on part of the output and constant at zero at another part, and this gives it enough nonlinearity for the purpose of a deep neural network, while at the same time speeding up backpropagation. But there is this part of autoencoders that was very explored when trying to solve that backpropagation problem, that is also useful for unsupervised learning. So in this last part of dedicated to unsupervised learning, this is mostly the focus of this lecture. If you want to use deep neural networks, you can, with Anaconda, use TensorFlow. This is being developed by Google. There's a lot of documentation here. It's based on Theano, so it's basically a re-implementation of Theano, and it uses the same kind of framework where you specify the graph with all the computations, then it gets compiled, for example, into the GPU if you're using GPU acceleration, and all the computations are run there. More recently, there is this PyTorch that is being promoted by Facebook, which is based on Torch, and here the computation graph can be generated dynamically, so you can change the computations during the run. It is not yet as popular as TensorFlow, and there are not so many examples and uses, and there is probably some loss in efficiency because of if you can specify the whole graph for the computations, it's easier to optimize than the compilation for that. But it can be easier to learn if you want to just experiment, because you don't need to learn about that design of the computation graph in one go and then get into run. Both of these can be installed easily in Anaconda, especially if you don't use GPU acceleration. If you want to use GPU acceleration, then the setup is a bit more demanding, but you just follow the instructions and it's not that hard. This is the end of the subject matter for this course. In this semester, we did not have any holidays on Tuesday, so we have one extra session because of that. So, the next session will be for questions mostly about the second assignment, because it will be on the week where you have to hand in the second assignment, and then the other one will be revisions and questions for the exam. Okay? So, this is the end of what you need to know. The next two sessions are just for questions.